Assalamualaikum warahmatullahi wabarakatuh and good day. So welcome back to my video, and we will continue with our topic number 2, still on the balanced three-phase system. So we continue with subchapter 2.2, three-phase source connection. Alright, where we will see the 3-wire star connected source followed by 4-wire star connected source. And finally, we will discuss about the 3-wire delta connected source. Alright, 3-wire star connected source. So Y connection or star connection has 3 voltage sources. This is what we have discussed earlier. So we have one common point, okay, to connect all the 3 phase RY as well as B, where the 3-wire leading away from the voltage sources windings. So away from the winding are typically called lines. So this is all called line because it is leading or leaving the winding, the coil. All right. So heading to the load. So this is what we call line. Okay. While the windings themselves are typically called phase. So all these 3 coil or all these 3 windings is basically called phase. Right? And all 3 wires in the 3-phase 3-wire distribution system, see figures, are all live wires. So these are all live wire. Right? So thus a 3-wire load can be connected to all three wires respectively. So we have our phase, which is connected to a live line between this phase and this live line, another phase and live line over here, so another phase and live line for B phase. So 3-phase 4-wire Y connection uses a common force wire, see figure. So the common force wire is actually referring to this line, okay, the neutral wire. So 3-phase 4-wire distribution. So again, 4-wire, the 4th wire always refer to neutral wire. So a distribution system may be designed to produce single phase or 3-phase voltages. So for example, a generator could produce 3 single phase for 240 as well as 3-phase 415 voltage. So this is one of the advantage for 4-wire distribution system, because it is able to generate single phase supply as well as 3-phase supply. Because single phase supplies, it is connection between Y and N, for example. So 3-phase, we have V4, R and Y, for example. All right. So this system is more flexible than the single phase system itself, and then used to supply power to structure that requires substantial amounts of power, so multi-level amount of power and lighting, such as shops, hospital, and all those big buildings. Right. So what about data connected source? So joins the coils as an equilateral triangle and applies the individual phases at each of the verticals. So they are actually equilateral between one phase to another in a triangle form or triangle shape. So an advantage of delta connection is higher reliability, because we know that V phase is actually equal to V line. Okay, so any disruption, any disturbance, so we have one failure over here. All right, so we have one failure over here, which is being grounded. So the system, the 3-phase system, will still remaining in a good operation, because the other two, this line, let's say it's line number 2 and line number 3, will actually cover, all right, losses caused by line number one, right? So this is why the system is much reliable. So if one of the three primary windings of the distribution transformer fails, so this is what I mean earlier, so the secondary will still produce full voltage on all three phases. The only requirement is that the remaining two phases must be able to carry the load. So let's say one coil is faulty over here, line number one, so line number two and line number three is still able to produce or to generate full voltage in order to suit with the three-phase load. So advantage of delta connected three-phase voltage source. Delta connected three-phase voltage sources give greater reliability in the event of winding failure than Y connected source, because we know again V line this is equal to V, so equal to the V phase. All right, any failure of one of the winding will actually give no much or no severe effect to the operation of the load. So this advantage for this delta connected, so have larger line current than Y connected, because simply VL, this, sorry, not VL, but IL, this is equal to square root 3 I phase. Alright, so that's why it is stated here that larger line current then Y connected source to deliver the same amount of power. Voltage and currents a three-phase circuit. All right, so notation and convention for three-phase circuit. So we have seen earlier in the previous slide. So this is how we give the notation and convention. So VRN, this is the direction of the voltage of VRN. So the arrow over here, the head is pointing to the line itself. R, for example, so this is the back or the rear of the arrow. This is actually where the voltage is coming from. This is point N or node N. So this is how we denote the direction of V for VRN, VVN, as well as VYN. So similarly for line, so direction of I is always, all right, towards the load. All right, always toward to load. So this is load station. All right, so this is load section. So current always coming from sources, generation, for example. All right, this is generation side or generation section. So coming or moving, flowing towards the load section. Okay, this is how the I neutral coming back to the source. All right, through neutral line. So ZL for the first one, second one, and third one. So this is similar to what we have seen for the notation and convention at the generator section. Okay, how they denote the subscription of VYN, all right, the arrow of the direction of the arrow, so as well as the second phase R, third phase B, etc. etc. So labeling convention for voltages and currents. So the relationship between line quantities and phase quantity for a given generator or load depends on type of connection used for generator and load. So type basically we have again star or delta. All right. So thus in this convention, VRN represent the phase between lines R and N, while VRY represent line voltage between lines R and Y. So particularly for star connection, again, so this is N node, all right. So VYN for first phase, all right. So VN for second phase, and then VRN for the third phase. So what about the line voltage? So VRY, so this is R, so this is Y, all right. So the subscript notation over here. So we start with R, okay, where the arrow is heading, and then the second notation over here, our subscription over here. So this is where or the origin of the arrow, all right. So R refer to here and Y refer to here, this line. So similarly, so we have VYB, so this means Y is over here, the first subscription, Y is over here, all right? So B is over here, and VBR as well. So line voltage VRY, VBR, VYB. So RR, IR, IY, and IB, so represent the phase or line current. Okay, for for star connections, remember, so we have R line which is equal to I phase. So direction of source phase and line voltage are always drawn pointing to the node. So this is what I have shown earlier. So identified by the first subscript from the node identified by the second subscript. So this system helps us determine the sense or direction in which a voltage is acting in any instant, and allows us to easily construct the phasor diagram. So by the same convention, so line current, R, I, Y, I, B are always drawn pointing to the load. So what about the star connected source? So value of EMF generated. So this is the back EMF or generated inside the winding of a generator. So three phases are ERN, EYN, and EBN. So VRN, VRYN, VRN, VYN, and VYRN denote the set of, so this is BBN actually, so BBN. So the set of three-phase voltage, while VRY, YB, and VR denote the set of line voltage. Again, so we have over here, so we have VRY, for example, right here. Okay, so this one also, right? So we have VYB, etc., etc. So this is for line voltage. Okay. So assuming a RYB sequence, so this is positive sequence. So just to recap, so we have RBY. So this is RBY. This is equal to negative sequence, right? Just to recap, okay? Assuming positive RYB sequence and taking phase BRN as a reference, so then we have the following phasor expressions. So we have R over here, right? So we have Y over here, and we have B over here. So we have the V phase between VR and N, okay, VY and N, as well as VB and VB and N. Phase voltage VRN equal to V0 angle, alright, because reference always 0. Okay, so you have taken VRN as the reference. That means the angle is 0 and V remain as V, the magnitude of voltage. So VYN, so this is V minus 120. So you can see from the phasor diagram, for example. So here we have VRN, and then we have 100 degree away the clockwise direction. So this is minus 120 degree. So we have the third one is VBN. So this is actually, so CW means positive. So we have positive 120 degree away from VRN, right? So line voltage, so VRY is actually equal to VRN minus VYN. So we have VRY over here. So this is actually VRY, this is actually VRN, okay, minus VYN. All right. So just substitute the value of VRN over here. You take these values, substitute or put it here. So VYN, you take this value and put it here. And then solve this equation, you will get VRY is equal to square root 3, 30 degree with angle of 30 degree. So similarly for VYB, So VYB is over here, which is VYB. So this is RY. So YB is somewhere here. So this is VYB. All right. So we have VYN minus V minus VBN. All right. So we have YN minus VN. So we have Yn minus Bn. So again, substitute value of Yn here to here, and Vbn, you take the value from here to here and solve this. You will get Vyb, it is equal to square root 3V minus 90 degrees. Similarly for VBr, the third V, so substitute the value of VBn and VRn, so you will simply get the value of this line, which is square root 3V minus the angle of minus 210 degree. All right. So for star connected system, line equal to phase current. So it's a figure. So we have no problem with the I. So this is the R line. All right. So this current is coming from this phase. Remember, this is the phase. All right. So this is actually I phase generated by this winding of this coil. So this I will also go to line current. So we have simply that IP is actually equal to I line. Okay. So the relation between phase voltage and line voltage can be analyzed using phasor diagram. So basically we have this value. So the basic value, the reference. So this is reference. So reference, that's why. So we have a 0 degree. All right. So we have 0 degree, VRN. So we have VYN. So the second phase. So this is 130 degree, 20 degree away. All right. So we have the third phase, VBN. So this is actually, so we go further over here. So this is actually minus 240 degree away, or we can simply say that this is actually here, from Yn to here, counterclockwise. So this is for plus or positive 120 degree. Okay. So so Vyn, so minus, okay, this is if you go opposite Vyn, so you plot or you drag, this is upward, so you got negative Yn from here. Okay. And then what about the line voltage? Okay, line voltage. So you have derived just now that Vry. So this is actually square root 3. All right. V with the angle of 30 degree. Okay. So this is actually Vry. When we come to the phasor diagram, so all this called phasor diagram. All right. So it is actually angle with angle of 30 degree from reference. Vrn is the reference at 0, so it is going upward by 30 degrees. So 30 degree over here. Okay. So V is longer Vry. You can see. So this is V for Rn actually. So this is V for Rn. So you can see that the value of Vry, okay, this is equal to square root 3 Vrn. So that means when you come to Vry, so the value is higher than the value of Vrn itself by square root 3. Okay, so once we come to phasor diagram, so how to represent the higher value? So make it longer. Vry is longer than Vrn. Okay, you can see the distance over here, the length over here between these two. So this is shorter, this is longer, because Vry is equal to square root 3 Vrn. Okay. So similarly, if you plot Vyb, all right, if you plot Vyb from the answer, so we have Vyb is actually square root 3 minus 90 degree. So we have Vyb, this is equal square root 3 V minus 90 degree. So 90 degree from Vrn here. So 90 degree. And then for VBR is minus 210 over here. All right, so the magnitude is same, square root 3V, but the angle is now relocated to minus 210 is over here. This is okay, minus 210. So thus we can say that for a star connected source, the line voltage is square root 3 times higher or greater than the phase voltage. That is VL equal to square root 3V phase. Any line current is same as the current in the corresponding phase. So here line current and phase current is actually identical or same. So example, given the following star connected source, find VRY, VYB and VBR. Right? So you need to find the value of line voltage. The given one is phase voltage YN, YNN, VNN, and RN, RNN. So draw the phasor diagram. So determine the phase sequence of this system. Alright, so how to solve? So from the source connection given, we can simply write that VBN equal to 100 and 0 degree here is over here. Alright, so for the first phase, so the magnitude is 100, so the degree is 0 degree. And then so the second one, so VRN, this is equal to 100 and minus 20 degrees, so the second one is over here. Alright, for the second source or the second phase, so this is 100 minus 120, and then the third one VYN is for the third phase. Alright, so this is the value, so we have 120 degree. So similarly, if you derive from what we have seen earlier, so VBR, this is equal to VBN plus VNR, so this is equal to VBN minus VRN. So we can simply substitute the value of VBN and VRN, so VBN and VBN into this equation, and then we can simply solve, right, the analysis, and the final value give you 173.2 with angle of 30 degree volt. Right. So now we try to plot the first line voltage, which is VBR. Okay, so VBR, so this is again equal to VBN plus VRN, okay, with the value of 173.2 volt. So VBN is actually 100, right? This is 100 volt with 0 angle, 0 degree angle, and then positive 30, so this is positive 30, all right, plus 30. All right, so this is how we plot VBR. But alternatively, we can very much shorten the solution step by using the fact that line voltage is square root 3 times greater than the phase voltage. Okay, we can say that the line voltage is actually square root 3 times greater than V phase. So all here is actually V phase. So to make it shorter, in terms of the analysis, we can simply write that, so VBR is actually square root 3 times 100 over here. Alright, so all these are equal. Alright, remember, so we are still in the balanced three-phase systems. Alright, so the angle and then the line voltage lead its corresponding phase by 30 degree. This means we just simply add up 30 degree over here. Alright, so multiply 100 by square root 3, solve this, and then it will give you 173.2. And then for the angle, so it's just plus 30. Alright. So similarly for VRY, right? So VBR, so this is coming from VBN. Okay. So for the second line voltage VRY, so this is coming from VRN. Okay, again, so 100 multiplied by square root 3, okay, and then minus 120 volt plus 30 degree. So they give you minus 90 degree. Similarly for BYB, so the last line voltage, this is coming from the third phase voltage BYN. So multiply 100 by square root 3 and then 120 plus 30. So they give you same magnitude of voltage but different angle. Alright, so 120 plus 30, this is equal to 150. So phasor expression for all phase and line voltage of a 415 volt 4 wire 3 phase supply, assume a RYB sequence taking one phasor BRN as reference and two second question phasor BRY as reference. Okay, so this is the solution. So given line voltage B line is 415 volts, therefore phase voltage, so we have 240. All right, so change the value instead of VL, now so we have V phase. Okay, so taking VRN as reference, we can write for a symmetrical balance for wire star connected, for example. So VRN, so 240 0, and then the second one 240 minus 120, and then the third one is 240 1 and 120. Again, for here, for example, so this is BRN. All right. So we have minus 20 degree away, which is VYN. And then this one is VBN. Okay. So for our RYB sequence, so we know that line voltage RY leads RN by 30 degree. All right. So this is what we have seen in the previous slide here. All right. So voltage by 30 degree. Okay. So for RYB sequence, we know that line voltage RY leads BRN by 30 degrees. Hence, we can simply write that for RY. So how to get 415? Because this is for phase. And then you multiply by, okay, multiply by square root 3. So you will get 415. And then with the angle of plus 30 degree or leads by 30 degree here. This is the statement. All right. So BRY leads 30 degree from VRN. Similarly for BYB, so from here, okay, to here, so we have 415 after we multiply by square root 3. So here we add up 30 degree, so we still get minus 90. And similarly for the third one, so this is actually minus, this is equal to minus 240. Alright, so 240 plus 30, you will get minus 210. So this is how it looks like. So VRN, your reference. So YN, so this is what I draw over here. Okay, RN, YN, and VN. So this is VRY, so plus 30. Okay, and then BYB is actually 415 minus 90 is over here. If you can draw, okay, this is BYB, and then the last one is VB. VBR is somewhere here with longer arrow. Okay, this is VBR. Okay, so you have done with the phasor diagram. And then what about taking BRY as a reference? Okay, we can write for a symmetrical balance source BRY. So now we change BRY as the reference with zero angle. All right. So just now we have phase BRN. So this is zero angle. All right. So once we convert or we transform to line voltage, all these three, so you can see the magnitude is changing, and then the degree also changes. Okay, so what about taking BRY, the line, so this is actually the line, V line, as the reference? So we can write for symmetrical balance source VRY, so 415Y, 415 for the line voltage, 0 angle. So VYB 415 again 100 minus 120, and VBR this is 415 120. Again, if you can see for a symmetrical balance source, they are always separated by 120 degree. 120, another 120. All right. So we have, because we have 360 for a full circle divided by 3. Okay, so we get equally 120 degree each. So this one we have VR, VRY, all right, referring to this. And then the second one over here, minus 20 is actually VYB. Okay, and then VBR is actually over here. So for a RYB sequence, we know phase voltage VRN lags VRY by 30 degrees. So the other way around, so VRN lags by 30 degree. Just now we have VRN, so we convert to VRY. This is the line, so we plus 30 degree. Right. So the other way around, so we have VRY the line, so it go to transform to VRN. So this is minus 30 degree. So this is for phase. All right. So this is for line. So this is for line back to phase. All right. So we have minus 30 degree. So we know phase voltage Rn lags VRY by 30 degree. Hence we can simply write, so 240, because we divide by divide by square root 3 here. So just now we have multiplication. So now we have division, which is divide by square root 3. All right. So minus 30, similarly for the second phase voltage, VYN from here. All right. So go to here. So again, divide by another square root 3. So, and then this one here, previous one we have here to here, so minus 30 degree. So here the second phase, here minus another 30 degree, and then the last one should go to here, minus 30, another 30 degree. This is actually equal to minus 240. All right. BBR from here to here, BBR, this is minus 240 degree. Alright, so this is VRN. So the one in red color, VRN, PVN, BBR. So you just draw the phasor diagram according to the position of the angle as what we have obtained in this solution. Okay.